Part A. X-rays are used for detecting cracks inside metal beams. Roman 1. State the type of X-rays used. And the X-rays that are used in detecting cracks in metal beams are what we call the AD X-rays. Why do we use AD X-rays? Because they have high penetrating power. We have high penetrating power. So Roman 2, we have give a reason for the answer above, and already we have given the reason. The reason is they are more penetrating, and their high penetration power is as a result of high speed. So they are produced by high voltage, hence high speed, and thus high penetrating power. Part B. Figure 13 shows the features of an X-ray tube. This is the figure 13. So we have an X-ray tube whereby we have the filament and the cathode. We have the electrons being produced and accelerated towards the target. So we are taught Roman 1 to name the parts labeled A and B, and our part labeled A is this part, and as you can see, these are the produced electrons from the cathode. So A will be the electron beam. So here A will be the electron beam. Then B is at this point on the other side of the target, and this is the anode. So B is the copper anode. Then we have Roman 2. Explain how a change in potential across PQ changes the intensity. So when we increase the potential between the points P and Q, the following effect will be observed on the intensity of X-rays produced in the tube. So when potential across PQ is increased, the temperature of the cathode increase. So normally in an X-ray tube, when you increase the potential difference, the PD, this will lead to high heating effect. High heating effect. And it is this increase in heating effect that will lead to production of more electrons. And the number of electrons in this case is the one that determines the intensity of the X-rays. So in this case, when potential across PQ is increased, the temperature of the cathode increases. This increases the number of electrons released, hence the intensity of X-rays. Then Roman 3, during the operation of the tube, the target becomes very hot. Explain how this heat is caused. And the heating effect that is observed in an X-ray tube is because of the kinetic energy being transformed to heat energy. So here we have most of the kinetic energy is lost to heat. This is because we have about 0.5% of the total energy being transformed to X-rays. So the rest of the energy is transformed to heat, and that is why the target becomes very hot. Then Roman 4, what property of lead makes it suitable for use as shielding material? And lead, we normally say that it has a high atomic mass. Lead has high atomic mass, and it is this high atomic mass that makes it to be dense or to be more dense. And the high density here is the property that makes it to be used as a shielding material, because the high density will make it be able to absorb any X-rays. So lead has high atomic mass and is very dense. This enables it to stop or absorb X-rays. Then part C, we are taught in a certain X-ray tube, the electrons are accelerated by a potential difference of 12,000 volts. So here we have 12,000 volts. We have 12,000 volts, not 1200. So here we have 12,000 volts. Assuming all the energy goes to produce X-rays, determine the frequency of the X-rays produced. We are taught to take Planck's constant H as 6.62 times 10 power negative 34 joules, and the charge on electron E to be 1.6 times 10 power negative 19 coulombs. So we have our solution. We know that energy of electrons the electrons produced is given by the quantity of charge Q times the voltage, and this same energy can also be given by Planck's constant times the frequency. Therefore, in this case, the quantity of charge is 1.6 times 10 power negative 19. We multiply by the voltage 12,000, and this is the same as Planck's constant 6.62 times 10 power negative 34 multiplied by frequency. And we are taught to determine the frequency of the X-rays. So in this case, we are going to divide both sides by the Planck's constant. So when you divide both sides by the Planck's constant, we will have F being equals to 1.6 times 10 power negative 19 times 12,000 divided by the Planck's constant 6.62 times 10 power negative 34. When you multiply and divide using a calculator, you will get the frequency as F being equals to 2.9 times 10 power 18 Hertz. So you have to express the frequency into its SI units. So our answer will be 2.9 times 10 power 18 Hz.